All right, welcome everyone to our fifth lesson of the semester. Last time we finished learning about how to integrate trigonometric functions, or rather powers of trig functions multiplied together. And a good deal of them were relatively straightforward. You can kind of just do a U substitution with one notable exception. That one's not great. But now we do know how to integrate a lot more trig functions than we previously knew how to do. Now, what we're going to do is we're going to apply that knowledge to integrate things other than trig functions, but we could use our knowledge of integrating trig functions to help us. And this method, this is lesson 5, this method is called trigonometric substitution. And I'm henceforth going to call it Trig Sub. Everyone calls it Trig Sub. And this is going to be part 1, and we're going to talk more about this next time. All right, so what is trig sub? Well, when we were doing all of these trig integrals before, we made use of one really powerful identity called the Pythagorean identities. And in those, we had sine squared plus cosine squared is 1. Or another way of looking at this is sine squared, 1 minus sine squared is cosine squared. All right, the other ones we had were secant squared minus 1 is tangent squared. And then we also had the cosecant version as well. So we're really not going to be using this one too much. So don't worry if you're a little bit confused at the end of last time. We're not really going to do too many cosecant integrals right here. So what we're going to do is we're going to try to substitute other things in for these trig functions. And when we do that, we can use these Pythagorean identities to help us out. So let's take a look at an example of this, and I'll show you what I mean. So let's say that we want to compute this integral right here. 1 over x squared times the square root of 1 minus x squared. Okay. Now, hopefully you guys learned in algebra that unfortunately we can't split square roots over squares. So the square root of a squared plus b squared is definitely not equal to a plus b. So we can't just take the square root of each of these and say it's 1 minus x or something like that. Unfortunately, we can't do that. So what are we supposed to do instead? Well, notice that this equation right here has a similarity to what we have up here. If this x were, say, a sine instead, then we could turn the 1 minus sine squared into cosine squared. And while square roots do not work well with 2 terms, they work very well with 1 term that's squared. So if we can do this conversion somehow here, then maybe that will help us simplify our problem. So what we're going to do is we're going to do this substitution. X is equal to sine of theta right here. And theta is like usually the common variable for trig sub, but you could really use whatever you want as long as it isn't x. So this is going to be our substitution. And this might seem a little bit weird, right? Because what's the other time we've done substitution? We've done u substitution. And in that case, we did u is f of x. So this is kind of backwards from how we usually do things. Usually we have the new variable as a function of the old one, but now we're going to have the old one as a function of the new variable. So this is a little bit backwards from how we usually do substitutions, but it's going to work exactly the same way. We're still going to do the substitution the same way as if we would with a u substitution. Okay, well, when we did do a u substitution, there was something else we needed to do before we could plug it in. What was that? Yeah, we need to find out what du is. So back with u sub, we did du is f prime of x dx. And we're going to do the same thing here. So we do the derivative of x. That's just going to be 1, and then we have dx. And then we do the derivative of sine of theta. It's going to be cosine of theta. And then we put a d theta right there. So just like we need to do the derivative for this substitution to get what the differential is, we need to do the same thing right here. All right, so let's go ahead and plug in this substitution and see if what I promised comes true, that this integral really does get easier if I make this substitution. All right, so let's see. So I have a 1 on the top here. And then on the bottom, I have x squared. But remember, x is sine now. So this is sine squared of theta. All right, then I have the square root of 1 minus sine squared of theta right there. And then finally, for the dx, I put in a cosine of theta. By the way, this is probably one of the easiest things to forget. It's really easy to forget to put in that extra cosine or other trig functions for other problems into our integral. So do not forget to include that, because it will be a totally different integral if you don't include it. Okay, so anyways, we have the integral of cosine over sine squared times root 1 minus sine squared. And at first glance, it looks like we just made it worse. This doesn't look any easier than before. For syntax, is sine squared, oh yeah, so I forgot to let you guys know about this. So I recently put up the homework for the trig integration stuff, but if you want to type into Chronos, like let's say you want to put in your answer as sine squared, you need to do it like this. Yes, so this is the correct way to do it. Chronos, for whatever reason, will not accept this. So make sure that you follow this rule when you're typing in your answers into Chronos here. I don't know why it does that. I don't know how they're going to fix it or anything, but yeah, it's just we have to live with that, unfortunately. Anyways, all right, we got that out of the way. Now we have this integral here. It looks pretty nasty, but we could definitely do some stuff to simplify this. What can we do to simplify things here? That's right. So remember, the whole point of this substitution was to use the Pythagorean identity. So what we're going to do is we're going to turn this 1 minus sine squared into cosine squared. That was the whole objective of doing this weird substitution. And then what's the nice thing that happens afterwards? We have the square root of cosine squared. So we just end up with cosine. So this square root and the square are going to go away. And we have cosine of theta d theta. And we have sine squared of theta, and then a single power of cosine, because the square root got rid of the square there. And then something also happens that's pretty nice. Those end up canceling out. So the cosine cancels out on the top and bottom, and we're just left integrating 1 over sine squared. Okay, so this actually did simplify after all. Okay, now how are we going to integrate 1 over sine squared? We talked about how to integrate sine squared last time. How do we do 1 over sine squared? That's right, yeah, 1 over sine is going to be cosecant. That's right. So this is the integral of cosecant squared of theta. And I want to clarify, while I said we won't use this Pythagorean identity very much, we will still occasionally see cosecant and cotangent in our actual integrals, but we probably won't use this identity too often. All right, so now we just need to integrate cosecant squared. And does anyone remember what that one is? What's the integral of cosecant squared? All right, yeah, the chat has it here. It's going to be negative cotangent of theta. We can't forget the negative. Oh yeah, plus c. All right, so we were able to do this integral. That's really nice. But as with u substitutions before, we can't just leave our answer in terms of theta. They asked us to do an antiderivative in x, so rightfully we should provide them with an answer in x as well. Now, how are we supposed to turn this back into x's? Well, let's remember what our original substitution was. We have x is equal to sine of theta, right? This is the original substitution right here. Unless to how you got to the substitution, like how I picked x equals sine of theta, I'm going to go over that after this problem. I'm going to give you guys like a way to know which substitution to do for each one. All right, so we have x is sine of theta. Now I'm going to do something a little bit weird with this. It's probably okay if I divide this by 1, right? Because dividing by 1 doesn't change the value of your number. Now I have sine of theta is x over 1, right? So it's represented by the fraction x divided by 1. But sine of theta in general is represented by another fraction. It's something over something. You guys remember what that something over something was from trig? That's right. Yeah, it's going to be opposite over hypotenuse in terms of sides of a triangle. So that's what sine is right here. So we need to kind of break out the old SOHCAHTOA if you've forgotten that. All right. So let's see what this looks like. So if I draw a triangle, a right triangle here, and I have this angle being theta, then my opposite side is going to be represented by x, and my hypotenuse is going to be represented by 1. Okay, well, that's all well and good. Why did I bother doing this? Well, I want to figure out what cotangent is, right? So I want to figure out what cotangent is in terms of x. Now, what's the opposite hypotenuse adjacent for cotangent? That's right. It's going to be adjacent over opposite right here. Okay, so that means for my opposite side, we already know what that is. I can just put x. But then the adjacent side, we actually don't know that one. We only got the opposite and the hypotenuse here. So if this is A for adjacent, how could I get what my adjacent side is going to be? Yeah, we could use the Pythagorean theorem. That's right. Yeah, it looks like chat's got it already. So, well, we know that a squared plus x squared, so the two smaller sides, has got to be 1 squared, or 1. So if I subtract x squared, I have a squared is 1 minus x squared, and a is the square root of 1 minus x squared here. So this is what my adjacent side is going to be. That means cotangent is equal to this, and that means we're pretty much done with the problem, right? Because we want a negative cotangent plus c, so that's just going to be negative this fraction plus c. And there we go. So there's our antiderivative of the function that we started with. So the moral of the story is by looking for things that look like Pythagorean identities and actually making them be Pythagorean identities, we could do integrals that we couldn't have done before. Like, I don't think there's any way we could have done this in Calc 1, if I'm not mistaken. All right, can we not do the inverse of sine of theta to get x? So yes, we could do that. So we could take arc sine of both sides, and then we have arc sine of x is theta, and then we could have plugged that into here. So we would have had negative cotangent of arc sine of x. But then you would have had to convert negative cotangent of arc sine of x into a function, and it would be this one right here. Why is it negative? Because the integral of cosecant squared is negative. The integral of cosecant squared is negative cotangent. So we need to put a negative on what we got over here. How do we recognize when to do this? I'm glad you asked, because that's exactly what I'm going to talk about now. So how do we know when to do this kind of bizarre method and a kind of a long method of doing integrals? So trig sub works when we have one of these three scenarios. We have a number squared minus a variable squared, and that was the case that we just had. It works when we have a variable squared minus a number squared, and it also works when we have a number squared plus a variable squared. So these are sort of the three scenarios that we're looking out for that will let us know that, yes, we can use trig sub. By the way, a is a number or a constant. X is a variable. But it could also be something else squared. So maybe it's like e to the x squared or something. It could also be something a little bit different from just x, but it's got to involve the variable, and it needs to be squared. Okay, so if we have one of these three situations right here, then we could use trig sub. Now, in particular, for our last problem here, it was case 1, where we had a number squared minus x squared, and that number that was being squared was 1. So when we have case 1 right here, what do? We make the following substitution. X is equal to a times sine of theta. So this is the situation here. And then this is the substitution we do in that situation. All right, so when we have this guy right here, when we have a number squared minus x squared, we take the square root of this whole thing, so just a, and put it in front of sine theta. What if we have this one right here? Well, let's see here. If we have this situation, we're going to do x is going to be a secant of theta in this case. And why is that? Well, if we go back to our Pythagorean identities earlier, we see that secant squared minus a number simplifies to be tangent squared. So in this case, we're going to make our variable be a secant, and then we subtract a number, and it's going to turn into tangents when we do that. And then we have our final situation here where we have these added together, and of course it also works this way because it's the same thing. Does anyone know what trig function we would decide to use for this one? Where we add a trig function squared to get another and get a number and get another trig function? That's right. It looks like tangent of theta is going to do the trick. Tangent of theta, we're effectively, what we're doing is we're taking the identity that we had earlier here, so this one, and we're adding 1 to the other side. So this is secant squared is 1 plus tangent squared. So if we have something, a function squared, and we add it to 1, we can end up making it kind of like a secant. And these are going to be the 3 different scenarios in which we can use trig sub right here. If you ever have any of these or something that kind of looks like these, you could probably come up with a trig sub to do it. Now, that doesn't mean that you want to do that. As we just saw, trig sub kind of takes a little bit longer to do. So if you see another method of doing the integral, I'd probably recommend that you do it that way. But if you don't know any other method and it has one of these 3 kind of configurations here, then I would recommend trying trig sub. Okay, so we just did a case 1 where we had a number squared minus x squared. Why don't we take a look at another example here? Well, actually, wait a minute. Sorry. Why don't you guys take a look at an example? That's the next thing we're going to do. So why don't we get some practice with this? And I know this is kind of a complicated thing, so feel free to ask me questions. Feel free to work with each other. Everything's fine. All right, so practice 1. So we're going to do the integral of x squared over the square root of 1 minus x squared. So effectively, this is the same example that we had last time. So this is the same integral that we had back here, only the x squared just moved to the top. So you could do this almost the same way as number 1, or exercise 1. Now I'm going to give you guys a hint for this one, and I'll explain it when I go through it. The hint is that sine of 2 times an angle is 2 times sine of the angle times cosine of the angle. This will probably help you out near the end. Go check that out near the end. All right, I'll give you guys a few minutes to work on this. And by the way, this is actually the only practice problem we're going to do today. There's not 2, it's just this one because these are kind of long. So this is the only one we're going to do for practice for Canvas.
Professor Manley, I got to the part where I have the integral of sine squared of theta over cosine theta d theta. Do I try and make it to tangent of theta times sine of theta?
So you may be missing something. Remember that the dx also has a cosine as well. It'll cancel with the bottom cosine.
Oh, yeah, I see it. Thank you.
It's really easy to forget that. Yeah, don't worry about it. That's right, Sage. You're on the right track there. It's okay, Matthew. We're going to go over this afterwards anyway. Takes a little bit to get used to this. What kind of formula sheet do we get for the exams? There is no formula sheet for the first two exams, but there will be for the third exam and the final. I'll explain more about that once we get closer to that. We have to do integration by parts for the integral of sine squared. So with sine squared, we use the half angle identity to turn that into something we can integrate. So I'll remind you what that is too. Sine squared of theta is 1/2 times 1 minus cosine of 2 theta. So that's how we integrate even powers of sines and cosines. For the people in here, am I writing big enough so that you can see that? Is that okay? Okay. I'll give you guys another minute or so and I'll start doing this. Well, you're almost right, Sage. It's not going to be 0.5x though. All right, let's go ahead and take a look at this. I want to make sure we have enough time for the other examples too. So don't worry if you're not finished yet. I know these take a long time. So what we're going to do here is we see this, right? And we see that we have 1 minus x squared here. So that's a number squared minus a variable squared. So if we go up here, that suggests that we should maybe use x is whatever the number is being squared times sine of theta. So for this case, we're going to use x is just sine of theta because this is just 1. All right, we always need differentials for whenever we do a substitution. So we do the derivative and we have dx is cosine of theta d theta. All righty, so let's go into our integral here. So we have x squared is sine squared of theta, and dx is going to be cosine of theta d theta. Meanwhile, on the bottom, we have the square root of 1 minus sine squared of theta. And remember, this is the whole point of doing this substitution, is so we can do this Pythagorean identity here. So 1 minus sine squared, as we saw in the last example, is cosine squared of theta. And then the square root here will cancel with the square right there. So then we have sine squared times cosine divided by cosine of theta. And conveniently, those guys will end up canceling out. So all we're really doing is now we're just doing the integral of sine squared. And based on my hint earlier, we should probably use the half angle identity for that because it's an even power of sine. All right, so I use this identity. So I have 1/2 1 minus cosine of 2 theta. Like that. All right, and I just pulled the 1/2 out, by the way, because it's a constant. All right, and then now both of these are something that we could have integrated in Calc 1, so I'm just going to go ahead and do it. So I have the 1/2 coefficient, and then the integral of 1, remember we're integrating with respect to theta here. So the variable we're going to get is actually just theta. Then we integrate cosine of 2 theta to get sine of 2 theta, and then we divide by 2. And now that we've completed the integral, we should have a plus c right there. Yeah, Sage is asking a good question. There's a singular theta that's not in a trig function. How do we convert that back into x's? And I'm going to talk about that in a second. All right, so yeah, well, let's talk about right now, actually. So remember, our original substitution was x is equal to sine of theta, right? And we want to flip everything back to be x's. Now, does anyone see a way in which maybe we could just get theta on its own? How do I get rid of this and just have theta on its own? All right, looks like some people in the chat are saying that we have arc sine. So remember, arc sine is the inverse function of sine, meaning if you plug one of those into the other one inside the parentheses, they're going to cancel out. So I have arc sine of x is arc sine of sine of theta. As I just said, those will cancel out, and we just get theta is arc sine of x. All right, so that's going to be arc sine of x. Now we need to see what's going to happen right here. So we have sine of 2 theta divided by 2 right here. Now it seems like, well, we know what x is sine of theta, but this is talking about sine of 2 theta instead. So there's not really an obvious relationship between these two here. So this is where the second hint comes in right here. We're going to use this identity. And by the way, this has the name the double angle identity. We're going to turn the sine of 2 theta into 2 sine of theta cosine theta. We still have the over 2 there. All right, so those will cancel out. And then now I have my angle matching what I had for my substitution. So that's good news there. All right, so let's see. So sine of theta, we know what that is. That's just x. And then we need to get what cosine of theta is. And then how do you guys think we're going to get what cosine of theta is in terms of x? Yeah, we're going to draw the triangle. That's right. So as before, I'm going to write sine of theta as x over 1. And as we discussed earlier, sine is opposite over hypotenuse. So we draw our little triangle right here. All right, and then the opposite side is x, and the hypotenuse is 1. Actually, this is literally the same Pythagorean theorem we had for the previous one. That means our adjacent side is the square root of 1 minus x squared. All right, now back to cosine. We want to know what cosine of theta is going to be here. So what's cosine? Well, cosine is going to be adjacent over hypotenuse, right? So here's our adjacent side. It's root 1 minus x squared. And here's our opposite, or our hypotenuse, excuse me, which is 1. So that means cosine is just the square root of 1 minus x squared. And there we go. Now we have everything back in terms of x, and we are all finished up with that. All right. I saw some people asking about this here, the sine arc sine thing. Remember the way inverse functions work. if you want to get rid of a function applied to a variable, you can apply its inverse function to both sides. So if these are the same, then they'll also be the same if I put them both into an arc sign, right? So I can put the x in there, then I can put the sign in here. And the whole point of inverse functions is that when you have one inside the other, they'll just go away and you're just left with the variable. So we have arc sine of x is arc sine of theta, and those go away, and we're just left with the theta right there. So the moral of the story is that anytime we just have a theta on its own, we're going to have arc something as part of our answer. Since we use sine for our substitution here, we have an arc sine. Maybe in another problem, we'll have arc secant or arc tangent or something like that. But whenever we have a theta on its own, it's going to be arc something because of that. All right, there we go. So yeah, you guys can type this in at home or later or whatever. All right, let's take a look at a case 2 one here. So let's see. So case 2, remember that was x squared minus. Oh, I labeled this differently on mine, on my notes here. I'm going to do case 3, which is x squared plus a squared. And remember, with this one, we're going to have x substituting in for a tangent of theta. Is 2 theta not equal to 2 times arc sine of x? Yeah, it is. But the thing is that if you put arc sine of x into here, it won't cancel out because there's the 2 in the way. So while that is true, it's not really convenient for us to use that fact. All right, with this integral right here, which one am I going to do now? I'm going to do the integral of 1 over the square root of t squared plus 4. Okay, so whenever I have my variable squared here plus a number squared, that's when I'm going to use tangent. So my variable that I'm squaring is going to be t. And then I'm going to have a number, and then I'm going to have tangent of theta. And what number do you think I'm going to use for this substitution? 2. That's right. It's the square root of this number. So t is going to be 2 tangent of theta. Now, just like all the other substitutions, we need to know what the differential is as well. So dt will be 2 secant squared of theta d theta. All right, now we have everything we need to convert this integral. All right, so dt, which is technically on the numerator here, is 2 secant squared of theta d theta. All right, now down here we have t squared. So we have 4 tangent squared of theta. Don't forget to square the coefficient as well. So we have 4 tangent squared of theta plus 4 down there. Why the 2 again? When we square it, we want the coefficient here to match the coefficient right there. That's why we take whatever the square root of this is, because we know we're just going to square it back again. Okay, now why do these need to match? Well, if they do match, they're in both terms. I could pull it out of this. So I have 2 secant squared of theta d theta, and I have the square root of 4 times tangent squared plus 1. Okay, now what I can do here, you see I have a 2 up here and a root 4 down here. Those will cancel out. So this and that under the square root will go away. All right, so now what do we have? We have this right here. All right, and then what's going to happen next? Yeah, so we're going to substitute in the secant squared right here. We're going to use the Pythagorean identity. So tangent squared plus 1 is secant squared of theta. And then as an added bonus here, we have the square root and that square going away. So we just have a single secant, or single power secant on the bottom. By the way, one thing I want to emphasize, and this is kind of like a really common misconception about trig sub, you do not need the square root in order to do this. The square root is kind of a nice thing to happen because you get rid of the square in your resulting trig function, but you do not need a square root in order to use trig sub. Like I could have done this exact same problem without the square root. I could have done that with trig sub just as easily. So that's one thing that kind of spreads around. I don't know who starts saying this, but you do not need a square root. You don't need a square root to use trig sub. You can use it anytime you want. Anytime you have one of those three situations I wrote down earlier, you could use trig sub, square root or not. All right, well, the square root was pretty nice here because we can get rid of this and we can get rid of that. And we're integrating secant of theta. All right. So let me ask you guys this. What's the integral of secant of theta? This is one of the Calc 1 ones. Yeah, it's natural log of absolute value of secant of theta plus tangent of theta. And then now we have to have plus c. Daniel's asking, why do we need 2 times tangent? We always want to put whatever the square root of this number is, the number being added to the square. We always want that to be here because we're going to put back in t squared, and we're going to square this 2 again to match up with the 4 here. So that's why we do 2. All right, so now we're ready to just go ahead and finish this off here. So we just need to turn this stuff back into x's. Now let's see, tangent of theta, that's actually pretty similar to what we had already. So that probably won't be too much work. T is equal to 2 tangent of theta. Now in the previous problems, we divided by this kind of 1 that we made up to turn it into a fraction. But this time we don't even need to do that because we could divide by 2 and make this a fraction a little more naturally. So tangent of theta is going to be t over 2 here. And now in terms of SOHCAHTOA, tangent of theta is what? That's right. It's opposite over adjacent here. All right. Now we don't even need the triangle to get this right here. So we have ln of absolute value, whatever secant is. We know that tangent is just t over 2. So we can put that in there. Now what we really need to figure out is what secant is going to be, and that's going to require us to do the triangle here. So let's draw our little triangle. We have theta. Let's see, our opposite side is t. Our adjacent side is going to be 2 right here. And then we have our hypotenuse, which I guess I'll just call h. So if we want to know what secant is going to be hypotenuse over the adjacent. So we do need to know what the hypotenuse is. Is there a way to see the minus sign on the problem? It never shows online. Oh, geez, I thought they fixed this. Yeah, so last semester, so there's like a special code that I typed the math in, and for some reason the minus sign isn't showing up. Yeah, thanks for letting me know about that. Has anyone here experienced that? Like I'm missing minus sign. Oh, so if you highlight it. Oh, okay, that's a good idea. Yeah, so a temporary fix is to let your mouse just sit on top of whatever the text is, and if there's a minus sign in there, it'll show up in whatever ends up showing up there. Yeah.
If you just zoom in on the web page, it'll pop up again. So we had that in our Calc 1 class where that was happening. So you just control and then assign, you'll be able to zoom in and make sure come back.
Okay, so we have the audience. Oh, and I guess chat too. Saying that you could also zoom in. I think it's like a pixelation issue. I think like the minus sign takes up like a weird number of pixels and then it just kind of zeroes out in some way. I'm not sure how that works exactly, but yeah, you could zoom in if you're missing a minus sign or it looks kind of weird. If you don't know what we're talking about, you probably don't have the issue, so don't worry about it. All right. So, yeah, there's never, yeah, like we wouldn't write like plus something. Yeah, that's true as well. All right. Anyways, back to this problem here. So we want to know what secant is, right? And secant is hypotenuse over adjacent. So we need to get the hypotenuse here. So let's use the Pythagorean theorem to get it. So we have 2 squared plus t squared is h squared. And if we take the square root of that, we have 4 plus t squared. Now this guy might look familiar. Where did we see root 4 plus t squared before? Where is this shown up? Yeah, it's shown up in the beginning of the problem. And that's one thing, that's one way to kind of check your work. So when you make the triangle here, this, or at least something very similar to it, should show up in your integral. So this should appear in your integral. If this does not appear in your integral, that means you may have made a little bit of a mistake along the way, and you may want to check your work here. All right, and by the way, the square root doesn't need to be there. So if the square root's missing and that's the only thing different, that's okay. But if the 4 or the t squared, for example, are different, then you probably made some kind of mistake. Should appear in the integral. Sorry about that. All right, so now that we know what h is, we can write down what secant is. Secant is the square root of 4 plus t squared, the hypotenuse, divided by the adjacent, which is 2. And that means we can finally put in our answer here. We have root 4 plus t squared over 2. And there we go. So we end up getting our answer right there. And if you like, you can combine those into one fraction if you want. Instead of doing the triangle, can you just copy from the start of the problem? I'd be careful about that because it may not exactly show up in this form here. So I would advise against doing that. All right, let's see here. And then our final example that we're going to look at is, I guess, type 2. Let's see here. Actually, wait a minute. How much time do we have here? 18 minutes? Because I have another. Oh yeah, I got tricked too. Yeah, yeah. 3:42 plus 8 minutes is the end. Okay, so there's another example in here of a type 2 one. I think I'm just going to skip that one for now, and I'll post the I'll post like a written solution of it later on. So yeah, we'll go back to that later. But I want to show you at least one of the type 2s. So case 2, if you recall, is where we have a variable squared minus the number squared. And in this case, we want to use secant as our trig function right here. All right. So what are we doing for this example? Let's do the integral of 1 over 9x squared minus 1 to the 3/2. Okay, now this problem is a little bit interesting because first of all, we don't have a square root. I mean, we kind of do. This is a square root cubed, but it's not quite exactly a square root. And then another thing is that we have a coefficient next to our variable squared right here. So this is going to make things be a little bit different as well. Okay, now for this one, we're going to make our substitution be secant of theta. Because we have the variable squared, or the thing involving the variable squared, minus a number squared. Now we can clearly see what the a is going to be. The a is going to be 1 for this because we have a 1 right there. We're going to have secant of theta. But then what do you guys think is going to go on the left here? It's not just going to be x. What do you guys think it's going to be? 3x. That's right. So whatever is being squared here, and remember this is technically 3x quantity squared, whatever this is going to equal the trig function here. So if you have something a little bit different from x squared, then whatever the square root of the whole thing right here is going to be equal to our trig function. Okay, but other than that, this is just going to work exactly the same way that all of the other ones did. I'm going to do the derivative of both sides. Okay. Secant of theta, tangent of theta is the derivative now. And then I'm going to substitute. Okay, so let's see here. So we have our integral. I'm going to divide both sides of this by 3 because we don't have an extra 3 laying around in here. I'm going to divide by 3. Okay, anyway, so we just have a dx here, And that's going to take the form of 1/3 secant of theta, tangent of theta, d theta. All of this comes just from the dx right here. All right. Then, let's see. So we have that. And then now we're going to substitute into here. So we have 9x squared. So that, remember, that's just this squared. So that's going to be secant squared. Then we're subtracting 1. And we have this to the 3/2 right here. All right. So now that we have this, what we're going to do is we're going to start simplifying here. Can we split it into 1 minus 3x, 1 plus 3x, then call 3xu, and then make this be u squared minus 1. Well, it'll be 1 minus u squared, and do it from there. Yeah, you could do that if you want to, but then you would have to do a little mini u substitution where you divide by 3. No, it wouldn't be. It would still be case 2 because it would be 1 minus u squared. You got them backwards. So you can't avoid case 2, unfortunately. All right, so let's go ahead and simplify this here. So secant squared minus 1 is tangent squared. Now, what's tangent squared to the 3/2 going to end up being here? So when we have a power and then we raise it to another power, we multiply the powers together. So 2 times 3/2 will give us tangent cubed. So that's what we're going to have here. All right, so that's what we get out of this. And like I said, it doesn't need a square root in order for this to work. All right, so then what we're going to do now is we're going to cancel. Okay, that's pretty nice. And oops, sorry, that doesn't cancel all the way. It cancels to a square. All right, so we have 1/3 the integral of secant of theta over tangent squared of theta. Okay, now this one's a little bit awkward looking. So normally secants and tangents go along together pretty well, but that's when they're in the numerator together. When one of them's in the denominator, one's in the numerator, we can't unfortunately use the techniques that we have from before. And if we did u as tangent, maybe du would be secant squared, but we only have a single secant up there. So what are we supposed to do? We can't use the techniques that we learned last week, and we can't use the normal u substitution. What are we supposed to do with this? One thing to kind of do when you're in doubt with a trig integral is to turn things into sines and cosines and see if maybe something will cancel out. So that's what I'm going to do here. Okay, so secant of theta is 1 over cosine, and then tangent is sine squared over cosine squared. Okay, let's see here. So 1 over cosine here, this cosine will cancel with one of them down here, like that, because I have 1 over cosine up here and technically 1 over cosine squared down there. So those will cancel out. Then notice that I have 1 over this fraction, right? So that means I could just flip this right ways up. And now this is going to be my integral instead. Okay, now unlike this integral, this is actually one that we can do. How do you guys think we should do this integral? Let's see. U sub, yeah, that's right. Yeah, so we could use U sub for this one. So U is going to be sine of theta, and du is cosine of theta d theta. And thankfully that works out really well because we have this cosine of theta d theta up here. So now this integral will turn into 1/3 the integral of du over u squared. Because remember, this all goes away into a du, and then I have sine squared, which is u squared. And then finally, I could just go ahead and use the power rule here. So what's going to happen is I'm going to raise this power of -2 to be -1. And then I divide by my new power, which is -1. So I have -1/3 times 1/u. Like that. Is this okay? Does anyone have any questions on how I got to here? Is this okay? Yeah, the point of this is that if you see some weird trig thing and you have no idea what to do, turn into sines and cosines. And more often than not, you actually will be pleasantly surprised by that. All right, now let's turn back into thetas. We have -1/3 and then 1/sine of theta. But then 1/sine of theta is cosecant of theta. So I think I saw some other people in the chat saying you could turn this into cosecant times cotangent. Yeah, you could do that as well, and then you'll end up getting here in the same way. I think it's a little bit, I don't know, maybe it's more obvious to some people, but I kind of think this is a little bit more natural here, but it's not wrong. Why is it 1/u and not u? This is technically u to the -2nd power. So if I do the power rule on this, I add 1 to my power to be -1, so I have u to the -1, and then I divide by it. So that's where the negative comes from here, and this is u to the -1. All right, so we're almost done here. Let's remember what our original substitution was way back when. 3x is secant of theta. And I can make this a fraction by putting a 1 right there. Now what we need to do is we need to get what cosecant of theta is. So we need to assemble the triangle and then read off what cosecant is, and then we're done. All right. All right, so here's our theta. What's secant again? Whatever what? Hypotenuse over adjacent. That sounds pretty good to me. All right. So then we have 3x here, and then we have 1 here. And then if we use the Pythagorean theorem, I think we're running out of time here. Oh, yeah, we have -2 minutes left. So I'm going to speed through the Pythagorean theorem here. We're going to get that, which, as I advised earlier, should match what we have originally, which it does. All right, and then I'm going to remember the cosecant of theta is going to be hypotenuse over opposite. So our hypotenuse is 3x, and then our opposite side, which we just computed, is this right here. These 3's will cancel out, and then we are all finished with that. So Trig Sub kind of goes the same way no matter which substitution you're using. You use the substitution, you can't forget the differential, you turn it into a trig integral, you do the trig integral, and then you use the triangle to turn everything back into x's. So don't worry if this seems kind of hard. It definitely is hard. It's definitely one of the harder integration techniques because we're going to get more practice with it next time. So we're going to be doing more Trig Sub on Wednesday, and we'll get additional practice with this. But yeah, other than that, I think we're all finished here. So I will see you guys then.